Hello and welcome to my talk on game theory, the free energy principle, and artificial intelligence. My name is Dr. Michael Harre. I'm from the University of Sydney, and I will be talking about a number of points that have been raised over the last 20 years or so, culminating in artificial intelligence models that have been produced in the last year. So we're going to start with games against nature, non-strategic games, and then move to how entropy and maximum entropy plays into strategic games in the game theoretical sense, and then Friston's free energy principle for cognition, and then how that relates to artificial intelligence and decision theory. And we'll talk finally about applications in artificial intelligence through Cicero's application to diplomacy. So in 2004, Grunwald and David produced a paper on games against nature using maximum entropy and minimum discrepancy for best reply in a Bayesian sense. And so in their paper, they were interested in expectations over log losses. And so the entropy, as we see in the first term there, is the expectation over the p distribution in terms of a log loss of p. And so this is an expectation of log losses. So you can then expand the notion of a log loss to the cross entropy, which is a log loss when the expectation is different to the argument of the log loss term. So p is different from q. And this cross entropy allows us to think about nature as providing us with the factor p and its distribution across states, and q, the agent making their decisions. And the idea here is what would then be the natural framework of log losses here. And what Grunwald and Dahl were able to show was that here the infimum over the expectation under the variation of q is related to the supremum of the variation of p on this distribution. And ultimately, their result led to the proof of the supremum of the infimum is equal to the infimum of the supremum in a min-max kind of argument for maximum entropy and minimum discrepancy for log loss games against nature. And so this was one of the first examples of the way in which this might work for games against nature with a non-interactive opponent, nature. And we can see how this works in practice here. We can see that with the cross-entropy term, we can vary the Q, and in varying the Q, we can see that the minimization of Q variation is achieved at precisely where the blue curve, which is the cross-entropy, meets the red curve, which is the entropy. And that it is achieved where Q is minimized is exactly the entropy term. And so the minimum discrepancy is achieved when Q minimizes the cross entropy term. So this allows us to have an entry point into log loss games against nature. In a similar way, we actually have maximum entropy arguments for game theory. In order to motivate this, we just want to talk briefly about the entropy term, which we see in the top term there, and its relationship to the potential function that's usually expressed in physics. So here we have Vp as the potential energy, and then we have what's called the Helmholtz free energy, which is F of P is the potential energy of the system less some factor temperature times the entropy term. And then it is the minimization of F of P, which then leads to the Boltzmann distribution in statistical mechanics. In a similar fashion, we have the entropy of a joint distribution in game theory, where we have two players, X and Y, and their strategy spaces over which we take probabilities. These are their action spaces, their probability action spaces as a joint distribution. And we also have the utility to each agent for taking actions X and Y. That's the expected utility across their action choices. And that leads to an alternative formulation of the functional that needs to be optimized in game theory rather than what we do in Nash equilibria. Here we have a functional where we have the expected utility minus some parameter T times the entropy. And here T doesn't represent temperature anymore. It represents uncertainty or error. So we have a bounded rationality interpretation of this form of game theory. This is called the free utility variation. Now, once we optimize the free functionals, we see that first term, P of x, is proportional to the exponent of negative beta Vp. That is the Boltzmann distribution. And below that, we have the equivalent Boltzmann distributions for game theory, where we have the probability of player X making their choices and probability of player Y making their choices is proportional to, again, some factor beta times the conditional expected utility now. And here, beta represents the inverse temperature. And so as beta changes, in fact, as beta gets larger, what we see is that the utility with the maximum value is then pursued by each of the players as beta increases. So what does this look like in terms of classical payoffs in two-person, two-choice game theory? Well, we have the expected utilities, so joint probabilities and then joint utilities to give our expected utilities across there. And then in classical game theory, it would be to choose the strategy which optimizes the outcome for each of the two agents from their selfish, self-regarding perspective. That is not the way in which we would do it if we wanted to recast the maximum entropy argument in terms of a Lagrangian, which is then allowed to result in not using free utilities, but maximum entropy arguments. So the Lagrangian here is that first term is the entropy plus a term of the expected utility multiplied by a Lagrangian parameter beta x plus beta 0 multiplied by the normalization constraint of the system. So this Lagrangian can now be optimized. So we take the partials of the Lagrangian with respect to the probability distributions, and then we solve for the probabilities, and we find that probabilities take the following form. These are the quantum response equilibriums. And so this is the maximum entropy Lagrangian approach to resolving what we saw just before, which was the free energy approach to modeling choices in game theory. So now we have multiple ways of approaching the task of deriving the quantum response equilibrium for game theory. This equilibrium actually has, for different beta values for the two players, a quite rich and complex topology in and of itself. This is a current research area which is producing some interesting and non-trivial results, even in simple games for game theory. We now want to just briefly touch on the approach that Friston's free energy delves into for understanding the way in which human cognition works. So here, this is just the free energy in physics recast. Again, it was what we had earlier. And then we broaden the definition of how it works in economics by having an expected utility. But here we don't necessarily need it to be strategic. We don't necessarily need to have two players. This is any utility optimization of any agent in economics, strategic or not. So, for example, consumer choice is not strategic. It's simply choosing the best basket of consumer goods, and the utility associated with that doesn't necessarily entail any sort of strategic interaction like as game theory does. So this is a slightly broader definition that we would have here. Now, that then gets recasted again as a free energy principle. Again, we end up with a utility less a constant times the entropy term, which leads to our traditional exponential variation. That leads to the way in which Friston imagined this to work. And so from Friston's perspective, he has states of the world that are observed and the actual states of the world, and that these can be the joint distribution, the probability of states of the world and their observation can be decomposed in a Bayesian way. But because, as is well known, the problem with the Bayesian approach is that it often is not an easy quantity to compute. We can turn it into an optimization problem by suggesting an alternative probability, Q of S, that then needs to be optimized by minimizing what will become our free energy for the system, which is Q, and that Q at its optimal value is an approximation to the probability of the state of the world given the observations that the observer has seen. And so this free energy that Friston proposes is the expectation under the distribution Q with the log loss of Q less the expectation under Q of the log loss with respect to P. So that first term, so that then decomposes into two terms. One is the entropy, and the other one is the cross entropy, the two terms that we saw at the beginning. And so what we can understand from this is that because the cross entropy term is always going to be greater than the entropy, then the free energy is always zero or larger, strictly non-negative. And so it is minimized then at the when P equals Q in the cross entropy term. And what does that look like from that diagram we looked at before? Well, as we see Q varying in the blue curve, we see that when Q is minimized and crosses the entropy, then the free energy will become zero as the blue line and the red line agree at that point. And anything where they don't agree to the left of that is going to be a positive value. Okay, now Friston then went on to write a very large number of articles on this free energy principle of the brain. But the core idea here is that the free energy principle that Friston articulated is a cognitive model of human decision-making, non-strategic. So it's much more in common with what we saw for games against nature in the Grunwald and Darwood sense. And so what we have here is Grunwald and Darwood's equivalence with the Friston's argument for the free energy principle. Okay, and then in the second box there, we have the game theoretical version of this, and the game theoretical version is the strategic interactions. So the first box has no strategic interactions. It's a game against a non-strategic nature. And then in the second box, we have two strategic agents playing against each other and no nature component to it. There's no background probability distribution. It's purely interactions between agents. And then, of course, in both of these boxes, you can then optimize these free functionals, and we end up with exponential distributions across strategy spaces. So in artificial intelligence, so moving away from game theory of economics and the Friston free energy principle of cognition, human cognition, artificial intelligence has a similar relationship using in the realm of Markov decision processes. So this is the standard setup for Markov decision processes. We have a state space and we have an action space. We have a transition model and a reward function and a policy which maps states and actions to real valued numbers. The transition model is a probability distribution between the next state S prime and its previous state S. We have the agent's policy, which again is a probability distribution between actions and state spaces. That takes the state space and produces an action. And then an optimal policy for pi between states and actions is a pi star that maximizes some expected accumulation reward. And so this leads to this value function, value V of S, which is simply Bellman's equation for policy pi. This is the optimal control parameterization for making a decision in game theory. and other control theory dynamical systems. Now, we can now start talking about how we frame this reward function in terms of a particular approach to constructing decision theory within reinforcement learning algorithms. And so in reinforcement learning algorithms, we have this equation here, this capital R, as a which is a reward function, which is a function of the state of the system and the policy of the agent, which can be decomposed into the reward for the state plus a KL divergence between the policy and the passive dynamics of the system. The passive dynamics of the system, of course, being related to the transition probabilities. What we can then do is construct a desirability function, which is then used to now define optimal control dynamics for our policy. And under those passive dynamics, we can now get a probability of the trajectory, which we can then turn into the control dynamics, which we can solve for. And here we have the probability of a trajectory, a control dynamics trajectory, given a starting point and a policy, a starting state of the system, S0, and a policy, and a trajectory through that state. So the probability of that trajectory through that state is the function that we see there in equation 44. Now, this is non-trivially related to what we saw before for Friston's free energy principle. So we have this reward function, which has an RS and a KL divergence term. We can decompose that into the utility functions for KL divergence, which is a log loss game for the term inside the lambda brackets, which is made up of an entropy and a cross entropy term, which is what we saw for Grunwald and Darwood. And we have a max-ent game theory, where the utility and the lambda times the entropy was the free energy that was optimized in the game theory argument, noting that it's game theoretical in this case, because specifically what we have is a utility for one player combined with the actions of the other players. So player I has a utility that depends on the policies of the other agents encoded in negative I. So the negative I is all of the other agents. And so what we see is that, in fact, this game space is decomposable into a log loss game and a max entropy game, and that in finding a solution to that, we have this probability at the top here, probability of an action dependent on the policies is this functional, this probability distribution at the top. And so what you want to take away from this is that we have a free energy principle, which is based on Grunwald and Darwood, as well as the free energy principle encoded in Friston's structure of decision theory for the brain. We also have a second structure, which is the free energy principle for game theory, the free utility associated with game theory. Those two different approaches are actually combined in the third box that we see here, where we have local maximum entropy game theory and a log loss game combined with an interpolation factor lambda, which draws them together. And so why is this most interesting to us in terms of artificial intelligence? Well, that brings us to the recent release of Cicero playing the game of diplomacy. Cicero itself is an artificial intelligence, and diplomacy is a strategic interaction game where Cicero was deployed to play against humans, but the humans weren't aware that they were playing an AI. It was an online game. And so Cicero was released into this online game environment, and it was sufficiently good enough that the people that were playing against it were only one person was even suspicious, and no one stopped playing because they believed they're playing against an AI. There was no serious detection of it as an AI. So, diplomacy itself is an interesting game in that its rules are simple enough to make risk look difficult, in terms of its rules, and yet at the same time, extremely nuanced game of strategy and cunning. So this is an exceptionally good test of artificial intelligence on a real world problem environment in which there is human-to-human interaction in a way in which things need to be communicated via not just strategic reasoning module that's obviously in there, and this is the focus of this talk, but also within Cicero, there was natural language processing. And so this is one of the first examples of a much more sophisticated version of artificial intelligence in which different modules that are responsible for different aspects of cognition, one natural language and the other strategic processing, are brought together in a single game theoretical artificial intelligence. But we note that the central point of interest as far as game theory is concerned is that the pickle, the PIKL regularized planning algorithm in there that's responsible for the strategy of this game is in fact equivalent to what we have seen just before in terms of the utility functions. And so we have here Pickle's utility function is an objective utility that both players have, as well as a KL divergence between what's called an anchor, which is tau, which is learned from the history of the game, and pi, which is the strategy, the policy that will be pursued by agent I. And we see that, in fact, it looks exactly like what we had before in terms of the free energy. So now this U, capital U, pi I, pi negative I, is in fact equivalent, entirely equivalent to the free utility that we were talking about before. And so we see from this that the key takeaways are that artificial intelligence are able to successfully, strategically interact with humans with a type of theory of mind, type of awareness of the strategy of other players. But strategy is only one part of the solution that made Cicero so successful. They need a language model as well as some filtering and human fine-tuning. It also requires grounding in an objective world. And only one player suspected they were interacting with an AI. So what's so important about what's going on here? Well, game theory is developing into far more complex environments in which people are strategically interacting with one another in far more realistic language exchanging environments, and that the strategic framework in which this is developed is becoming exceptionally successful when appropriately framed and deployed. It's also one of the most flexible approaches to date using these maxent theories for understanding how to construct the probability distributions over strategies in this interacting environment. It also provides us a connection between AI and human intelligence. We have now a way to connect what Friston did with what we are now trying to do with our artificial intelligence is playing these more sophisticated games, and that we expect to see far more complex tasks being tackled in the near future. And so that's all I have to say